How's your understanding of assignment 2 going? You having questions that we can dig through right now? Wow, 3 went up at the same time. Let's go 1, 2, 3. I've been seeing questions like that floating around, and I think to myself, what the heck is a my state? There's no my state in A* search, and that's because I wrote these instructions a long time ago, and this is an example. But just to be clear, don't use the word my state when talking to someone outside of this class about A* search, because there is no my state. That's my bad inability to come up with an intelligent class name. This would be, but in A* search, you're going to need some kind of a state class, and I got tired of students coming up with bad designs, so I wrote one for you. You don't have to use exactly this one. I'm just trying to give you a hint here. Notice that I have a cost of how far you've cost so far, parent, which really means the previous state, the one this state was generated from. So this makes a linked list back to the starting point from the goal. And then there's this state thing. I was trying to be really general here by suggesting that this algorithm could be used to solve any problem. In this particular problem, the one you're writing, the state is just 2 numbers. It's the XY position of the robot on the map, which is the answer to your question. I could have just said that. But so in your implementation, this is X and Y. But if you want to be really general, if you like to separate the general code from the specific code, which I really hope you do because good programmers will separate the general from this problem-specific code, then you'll make another class that inherits from general purpose state called problem-specific state. And the problem-specific state will have an X and a Y here because that's what we have in this problem. And then when you repurpose your code for solving some other challenge, like solving a Professor Layton puzzle with 11 pieces, then this state would be 22 bytes instead of 2 floating point values. So you should probably just use float x and float y in lieu of this state position. Notice I wrote a constructor here, and my constructor ignores the parameters. Obviously, that's not done, so you probably should stick cost into cost, except I shadowed a variable, so that's even bad practice. Yeah, you have to clean up my code a little, sorry, but that was trying to be helpful. The question is, why 2 comparators, and how is the comparator for the queue and the set different? So inside of our planner, we have what I'm calling the queue. It's actually a priority queue. And we have something called the set, which I'm calling bin there instead of frontier. Yeah, let's talk about that. So what is the purpose of the queue?
Give the lowest cost.
Yeah, it's to represent the frontier. It's to represent the places you need to go to next. It exists because you can't search everything in one shot in a serial computer. You can only think about one thing at a time. So the reason we use this queue is, hey, I want to explore that way, and I want to explore this way, and I want to explore that way. But instead of getting overloaded, we'll just say, okay, I'll do those 2 later, and I'll do this one now. And you go do it. And then you say, oh, I want to try that way and that way. 2 roads diverged in a yellow wood and have to go both ways. What should I do? Push one onto the queue, or put one in the queue and go both ways, and that made all the difference. So the point of the queue is to remember what to do. It's your to-do list. The point of the set is because you don't want to go somewhere twice, right? If you took the left path and you ended up at Walmart, and you took the right path, then it wound around and took you to Walmart. There's no reason you have to explore Walmart twice. You already know what's in there, groceries and clothes and stuff. Another over-specific example. Point of the set is keep track of where you are. Okay, why do these sets need to be sorted differently? That's the real question we're getting to. Well, they perform different functions. The been there set, the visited nodes, the closed set, whatever you want to call it, it has done its job correctly if it tells you, yes, you've been here when you have, and no, you haven't been there when you haven't been there, right? The priority queue is doing its job correctly if it's always giving you the shortest path to explore next. And why do we always explore the shortest cost path, or the lowest cost path? Because we're trying as hard as we can not to find the goal. Why are we trying so hard not to find the goal? Because by the time we finally find it, we'll know there's not a better way. Because if there was, we would have found it. Okay, so we're always exploring the lowest cost path so that we'll explore everything that could be a better path until we find the one that is the best path. And then we know it's optimal. Do you see that everything on the frontier, so if we were to draw a frontier, this is the frontier of cost, and this is the starting position, and this is where we're going, trying to get from the x to the o. It's probably going to go like that or something, right? But do you see that everywhere on this frontier has the exact same cost? So the only way this queue is going to work, this priority queue, is if it's sorted by cost, because we want the next thing to come out of it to be the lowest cost, right? What if we use that same comparator in the set of where we've been? Can you see that every single state on this frontier has the exact same cost? Therefore, if we're comparing by cost, we've been to every one of them before? Well, that's exactly the opposite of what we want. Those are all the places we haven't been yet. Those are all the places we need to explore. So they're almost performing opposite tasks. And if we were to use the same comparator for both the set and the queue, well, they'd both be sorting the same way, and either the queue wouldn't be giving you the lowest cost one first, or the set wouldn't be giving you unique example, whether or not your state is unique. Therefore, they must be different. Yes, except in this case, we're discretizing by 10 pixels at a time. So in fact, it should be 120 by 60 states at the maximum, which is a pretty small number. So your set's going to be relatively small this time around. So the queue maintains how much it cost you to get there, how many lakes you had to walk through and rocks you had to climb, and all of these paths that get from the start to the frontier should have the exact same cost. Down here, apparently, it must be easy walking. There must be a nice walking trail to get down here. Whereas up here, see how the frontier is close to the starting state? So there must be a cumbersome lake to get through right there. Yes, in the frontier, we're storing all of these states. And in the set of where you've been, we're storing all of these states. So the set will always be bigger than the queue, except at the very start. And that's cool. But they do need to be sorted differently. Technically, that's possible. However, the best implementations usually put everything in the set the same moment they put it in the queue. Everything that's in the queue is also in the set. So therefore, I'm going to claim no. But it's possible to implement it with slightly less memory usage by keeping them separate and using some kind of weird queue that's rapidly indexable. A common mistake people have made is asking the question, is this state contained in the queue? And they're using a linked list for the queue, and that's really going to make your program slow to a crawl, because how long does it take to find out if something's in a linked list? Order n time. You got to run through the whole darn linked list. Well, halfway through it on average. But that's very, very expensive. So if you add everything from your queue also to the set, you can efficiently query whether you've seen it at all yet. And that'll get you there quickly. I'm still going to get to you, but I've got to finish this question. The next part of the question was, and how do we implement two different comparators, right? So basically, let's go back to the assignment 1 instructions. Down here, I give you an example of how to implement a comparator for state. And notice how this comparator works. I run through all 22 dimensions and compare every single one. And if any of them are less than or greater than, I'm going to return a -1 or a 1. The only possible way you'll return a 0, meaning, yes, we've seen this state before, is if all 22 values are exactly identical. Okay? In this particular problem, in problem 2, the only case where you should return 0, meaning that these two states are identical, is if the x position and the y position are the same. Okay? Do we care about the cost? not for the been there set, not for the set of states we visited, because we're not testing what the cost is. We're testing whether this state has been visited before. When you make another comparator, so we'll just copy this class, Pwink, Pwink. You'll make two classes. This will be called the state comparator, and we'll make the other one called, how about, cost comparator. And then this one shouldn't compare by state. This one should compare by cost, so it'll be something more like return a.cost is less than b.cost. And that way, you've got two comparators. So when you're implementing your data structures, you'll say cost comparator comp2 and state comparator comp1. I'm sort of switching to C++ mode now. Let me do Java equals new state comparator. And don't forget the generics arguments, which I'm forgetting right now. Oops, I forgot. And then you'll implement your set, new set comp1 to use that comparator, and you'll implement your queue to use comp2. So now I've made two comparators, yeah. Yeah, good point. This isn't actually totally complete. It should be more like if a.cost is less than b.cost, then return -1. Pretend that says return. Else if a.cost is more than b.cost, return 1. Else return 0. Something like that. Yeah. Don't copy this code and just paste it in your assignment. Understand what I meant and rewrite it yourself, please, because I got in a little bit too much of a hurry there. The idea of a comparator, let's just get to what is a comparator. This is a Java thing. It's not a AI thing. It's a object that Java collections are going to use to decide how to sort stuff. And the purpose of implementing a comparator is to tell the Java collection how you want your stuff sorted. And our stuff needs to be sorted two ways, both by the state and by the cost, because we're using it in two ways, and you'll be using two data structures. Have I nailed that question pretty much? Awesome. Okay. Sorry, I know you're waiting, but let me get to one more thing I got to say on this. Tree set is a magical data structure that most programming students don't seem to know how to use effectively. And I just want to extol the virtues of a set, or a tree, or a map if you prefer. Tree set and tree map. Did you know they're actually the same data structure internally? It's just the stuff you're storing in them could be a pair of things, or it could be a thing. Either way, it's just a set. So we'll just call it a tree set for now. You know how a tree is structured, right? It's a balanced tree. So if you add too many things to it, it will always rebalance itself to be a nice flattened tree like this. And everything inside the tree ends up in sorted order. So this could be a 1, and this would be a 2, and this would be a 3, and this would be a 4, and this would be a 5, this would be a 6, this could be a 7, if you stuck integers in there. But it's sorted according to the comparator you provide, right? Do you see how a tree can actually be a priority queue? Because in fact, there is a method in the tree set class, and let me show it to you, Java tree set, that returns the lowest element in the whole set. Anybody know what it's called?
Root? Pull first one?
It's not root. Root will actually return this one, which is not the one you want. That's kind of the middle one-ish. It's almost a median, but not quite. Pull first. There you go. Retrieves and removes the first lowest element. So this basically pops out of a priority queue. And if you do insert, I assume there's an insert. Oh, there's an add method. Okay. Add adds the specified element to the set. So between add and pull first, you've got a priority queue with a tree. Right? Now, why should you not use a tree for your priority queue? Because heap priority queues are faster for insertion. Why should you use a tree for a priority queue?
Faster insert?
So a heap-based priority queue is going to be order 1 for insertion and order log n for popping out of it. And if you understand data structures, you'll know why. Because basically, the insertion amortizes out because there's 50-50 chance you won't have to bubble up to the next level in the heap. With the tree set, insertion is order log n, and popping is order log n. And hey, that's slightly worse, so trees are slightly worse for priority queues. However, log n is almost the same as constant. It doesn't make much of a difference, and trees offer some value that you can't get from a heap-based priority queue. Specifically, you can find an element in it and remove that element, and you can't do that with the heap-based priority queue. In this assignment, there is a case where you need to remove elements. Right, it occurs here. If you find a new path to some state, and that new path costs less than the old path, then you have to reparent that state. If you do that, it's really important that that state is updated in your data structures so that your algorithm's still working properly. So I'm going to say for this assignment, you don't really want a heap-based priority queue. You want a tree-based priority queue because it provides all of the operations you actually need, including you can find an arbitrary element in your tree, delete it, or fix its cost, and then reinsert it in the tree, and that keeps your data structures nicely clean and organized.